Good morning. Today we are going to start the next application of derivative, which is tangents and normals. As you all are already aware, the derivative of a function at a point gives us the tangent to the curve at that point. So let's quickly do a recap of this concept, which we did under the heading of geometrical interpretation of derivatives. Now let's take a continuous curve. So it will have some graph something like this. Okay, so let's take, this is y is equal to fx is the curve which we are taking. Now let's take any point P on the curve given by x comma y. Okay, so y is fx, so we write it as x comma f of x. This is the coordinate of this point. Now if let us give an increment delta x to it, okay, so that it reaches the point Q, and the coordinates of Q are x plus delta x and y plus delta y, which can be written as x plus delta x and f of x plus delta x. Okay, so let's join the line PQ. Okay, now the ratio of fx plus delta x minus fx upon x plus delta x minus x, which is what? The change in y coordinate with respect to the change in x coordinate is nothing but the slope of line PQ. By definition of slope of a line, we know that the change in the y coordinate upon the change in the x coordinate is the slope of the line PQ. Now let's proceed towards point P. I mean, as delta x tends to 0, the point Q tends to point P, and what happens is it goes here, it approach as delta x approaches 0, this point Q approaches here, then here, then here, then here. So ultimately this, when it reaches P, or when delta x becomes 0, the line PQ is nothing but the tangent to the curve at the point P. So as delta x tends to 0 or Q tends to P, line PQ becomes tangent to the curve y equal to fx at point P, but limit delta x tending to 0, fx plus delta x minus fx upon this gets cancelled, and over here we get delta x, but this is nothing but derivative of the curve at this point P. Okay, and it implies that derivative of y equal to fx gives us the slope of the tangent to the curve at that point. Okay, now taking this concept forward, we come to this conclusion that given any curve this, okay, at any point we have, this is the tangent to the curve. Now we also know that what is the meaning of normal? Normal is a line which is perpendicular to the normal to the curve at a particular point is a line which is perpendicular to the tangent to the curve at that point P. Okay. Now in order to, so this concept helps us in finding the tangent and normal to the curve at a particular point. Now from the concept of straight lines which we did last year, you all are already aware that equation of a line passing through a point x, let's say x naught, y naught, having slope m is given by y minus y naught equal to slope times x minus x naught, and this gives us equation of tangent as y minus y naught equal to the derivative at x naught y naught into x minus x naught, and the equation of normal will be equal to, the point remains the same, but now the slope becomes minus 1 upon the slope of the tangent, and the reason behind it is tangent and normals are perpendicular to each other, and the relation between the slopes of two perpendicular lines is m1 m2 equal to minus 1, or the slope of one line is minus 1 upon the slope of the other line. So here this is the slope of the normal to the curve at that point into x minus x naught. These two are the main things which we will be doing here. So basically we will be given a point at which we have to find the tangent and normal, and finding it means nothing but finding the derivative of the curve at that particular point, which gives us the slope of the tangent to that curve at that point, and minus 1 upon that derivative gives us the slope of the normal to the curve at that point. Now these two equations we have to deal with in this topic. So let's do the related problems.